Okay, I'm going to do three different examples that help relate the energy and work and pull things together. So we're going to start with looking at work. And I'm going to use a barge being pulled down a channel where I've got two mules, and these are mechanical mules. They're, like little trains that are going to pull this barge down the channel. And you can see that the forces are going to be unequal between the two barges, between the two mules. One mule is going to be pulling with a force of 500 newtons at a 30-degree angle, and the other mule is pulling with a force of 750 newtons at a 25-degree angle. And we're going to move this barge 300 meters down the channel. And we want to determine the work done to pull this barge. So the first thing that we're going to have to do is we're going to have to figure out the resultant force. So we can do that. We're going to use that mule 1 was 500 newtons. We got to deal with its individual components, its X and Y components. Same thing for mule 2. We got to deal with its X and Y components, and we're going to be able to calculate that resultant force. And the resultant force in this case is 1,113 newtons in the I direction and negative 67 newtons in the J direction, for an overall magnitude of 1,115 newtons at an angle of minus 3.4 degrees. So these two, even though they're unequal forces, it's giving us mostly in the downward direction of the channel. So if we do that, and if we remember that work is equal to force times the distance times the cosine of the angle between them, we can readily calculate the work. But this is a great problem to look at the vector mathematics. And if we look at our vector mathematics related to dot products, the dot products between any vector A and vector B is going to be a scalar, which is one of the reasons why we like going to using work and energy, because we don't have to deal with that vector notation anymore. So we have that AX times bx plus ay times by plus az times bz for a three-dimensional vector is going to give us our resultant scalar product. We can also look at a couple other rules. If I have two vectors, vector A dot product with vector A, I get A squared. I can do the reverse, A dot B is equal to B dot A, and I can use that commutation type rule. So let's do it with the vector type, and if you really want to review this, see section 9.3 in the CATS text. So if I've got my vector D, which is the distance down the channel, it's going to be 300 meters, so that's my vector in this vector notation, and I have my force vector in its notation, and if I go back and I look at how we deal with those scalar products, I'm going to get the 300 times the 1,113, and I'm going to end up with the same result as 3.34 times 10 to the 5th joules. And so if you want to go back and just verify that, yes, that is actually the same result, there it is for that particular problem. All right, so let's look at a different example here. This time, we're going to get a ball that's given a mass of 8 grams, and we're going to want to find the distance that the ball will slide up the inclined plane if the spring at the bottom is compressed 4.6 centimeters prior to releasing. Think of a pinball game. We're going to pull that pull that spring back. It's going to connect with the ball, and it's going to roll up to the top of our pinball machine, and then it's going to kind of cascade down. And in this case, we want to see what's that distance that the ball is going to roll up if we're at a 40-degree angle. We're going to neglect friction this time, and we're going to neglect any loss of energy when the ball is impacted by the spring. So the first thing that we're going to have to do is we got to think through the problem just a tad bit. We're going to use conservation of energy, and so whatever potential energy we're going to put into the spring is going to be the energy that's imparted into the ball, and then whatever that energy is going to result in how far the ball is going to be able to go up to the top of the incline. So let's look at our potential energy of the spring, which is 1/2 the spring constants times its deflection squared. And one of the things we have to do is we have to make sure we're in the correct units. Otherwise, things go to heck in a handbasket really quickly. So we can go in and we can calculate that all the way together, and we're going to end up with 0.0317 joules. And just to show the unit analysis, I end up with a Newton meter. That Newton meter comes together, and we know that that's defined as a joule. So now we know that that's equal to the potential energy at the top of the incline. So that's going to be our MGH. And we go through and we calculate what H is. But I want you to look at the picture. H is not equal to the distance up the incline. Let's look at this picture again. What we just calculated was this H. What we want is this D. So we're going to have to use our trigonometry in order to get the answer for that part. So we'll come down here and we'll look at it. D is going to equal our H divided by the sine of the angle, and we find out that the ball will actually go up 0.63 meters to the top. So now we're going to complicate things a little bit more. So let's look at this system here. We're going to have a ball that's going to start from 0.8 meters from above the surface. It's going to slide down to our horizontal surface there, and then it's going to cross 2 meters of very, very rough terrain, and it's going to hit the spring, and it's going to compress our spring that has a spring constant at 160 Newton meters. So let's kind of look at the statement of the problem. We're given a 10-kilogram ball that's going to slide along the track. The track is smooth, and when we see something like that in a physics problem, that tells us that we can neglect friction. And so we can assume no loss of friction until it hits that roughened surface. The ball then travels 2 meters and then hits the target, and we want to find out how much the spring is compressed at the end. So first of all, what's the energy of the system? Well, the energy of the system is going to equal that potential energy that's put in at the top. So that's our 10-kilogram mass times 9.81 meters per second squared times 0.8, which is how far above the horizontal it is. And so we end up calculating 78.4 joules. But that's going to equal our kinetic energy at the bottom just before it hits the rough spot. So now we're going to use our work energy theorem to help us figure out the energy that's lost due to the friction. Or in this case, what's the work being done by friction? So we're going to look at the magnitude here. So work is equal to the force due to friction dot product with that distance, or in this case, it's going to end up being the magnitude of, remember, friction is fun, mu times the normal force times the distance, and we calculate that the work done by friction is going to be our 0.3 times our 10 kilograms times 9.81 meters per second squared times our 2 meters, the distance that it goes across the rough surface, and we find out that the work done by friction is 58.8 joules. So the energy at the time that we hit the spring is going to equal our kinetic energy at the start minus the work done by friction, because that's energy that we lose, and we're going to hit the spring with an energy of 19.6 joules. So we're going to make the assumption that all that energy, that 19.6 joules, is going to go into compressing the spring. So when we do that, we can use our potential energy of the spring equation, which is 1/2 kx squared, and we put it in and say that it equals that 19.6 joules, and then we can go ahead and turn it around, solve for x squared, and when we do that, we get the 0.245 meters squared, take the square root, and we end up with 0.5 meters. So hopefully these 3 examples will help you do your homework problems.